Circular economy solves a lot of problems. Why wouldn't we all go circular? Welcome to watch the Sustainability Trends in Business. Today we will talk about how and when to reuse natural resources. The traditional industrial way of using resources is called the linear model. Linear model starts by obtaining some possibly non-renewable resources. These raw materials may be, for example, water, minerals, biomaterial, and so on. These materials are refined, which creates some side streams that end up as waste. For example, mining results in large amounts of rock, possibly chemicals. Well, then we have the refined material which we wanted to have, and they are used in the manufacturing process, which again usually results in waste of some sort. And then finally we have the product we wanted to have and we use it. After the use phase we discard. But then the use phase is of course the utility of the thing, but that may result in waste as well. This is of course a simplified model, as there are many different material streams combined in manufacturing, so the supply chains are complicated and there may be a large number of steps from the natural raw materials. But still, the principle is the same. Every time you get something in, something out, you get waste, which you discard and throw away. And finally, after use, the product is disposed and its end-use destiny is the waste bin. Well, you don't need to be a rocket scientist to tell that this process is not necessarily very sustainable. Thus, we have the circular model. We have here a couple of new boxes and no waste. So after use, the product is reused, possibly by someone else, for example, and it can be reused and reused several times. In the best case, it's upcycled, not recycled, but upcycled into something even more valuable. The upcycled product can of course be reused, or even upcycled. Finally, when the Grim Reaper is there, and it is the final power of time, the parts and materials are recycled into new materials to be used in manufacturing. By the way, there are layers of recycling. The less processing it needs, the better. But this is about using and reusing. This is a beautiful closed loop process. Who wouldn't love circular economy? Until some bloody degrowth guy, you know them, steps on the stage and says that the most important one is missing in this picture, and the most important one is don't use. A good example is the textile industry. There are approximately 100 billion clothing articles per year globally. 100 billion. It's quite difficult to find solid data on them, but this European Environmental Agency report tries to find out which part of the clothes are discarded before first use, so that no one uses them, no utility there. The long answer is in the report, but the short answer is maybe 1/3 of the clothes that are manufactured are never used before they end up as waste. They are out of fashion, they are in the wrong place, wrong size, wrong color, whatever. Or this Harvard Business Review article, The Lingering Cost of Instant Fashion, states that Shein, that is one company, had 1.3 million new products, no, not new, items, but new products added in a year, and that the sales target for 2025 is $50 billion. Well, I can just guess the average price of an item bought from Shein, but it cannot be much more than $5, which would result in 10 billion pieces of clothing. One company, 10% of all clothes in the world. The article is really worth reading. It outlines some marketing strategies, but it's not relevant in this context. Now, with this in mind, is the problem solved by a circular economy? Not likely. So, in this case, don't buy should always be the option number one. Well then, a completely different complaint against this circular economy comes from the physicist, because a true closed loop exists only with completely reversible processes. Well, reversible sounds theoretical, but a reversible process means that it can run either way, And if it consumes energy one way, it will release the same amount of energy when it's done the opposite way. And reversible and irreversible processes, if you, for example, drop a glass and it goes into shatters, it's quite reversible, for example. Or you can think of running something that happened backwards on film. If it looks somehow reasonable, then it's reversible. And if it doesn't make sense, you don't have reversibility. And now, almost all processes, if not all processes in circular economy, are non-reversible, irreversible. And hence, circular economy needs at least energy to be put in there. It is also important to understand that most recycling phases lose material. You need to top up the cycle with virgin material. So this pure cycle looks beautiful, but it doesn't exist. And upcycling, which is important and beautiful here, it's a great idea. But let me think of an example. I'll get back to that once I'll figure one out. It's very, very rare. At least someone may post Instagram photos of them with a dress made out of something upcycled. Looks great, but the example is far from scalable. If you have 5 of them in a year, no win. There are also some quite interesting social obstacles against reuse. Again, back to textiles. Who would like to buy second-hand bed sheets? You know, people have slept in them, people have possibly done something. Well, let's not think of that. Anyway, no, we won't. But would you like to stay in a fine hotel? Wouldn't you? And the sheets in a fine hotel, let me think. So, cultural questions are not always about logic. While circular economy is a great idea and a target, it can go wrong. This is a satellite image of the Aluminium shipbreaking yard in Gujarat, India. Old ships are run ashore and then they are broken. The working conditions in these shipbreaking yards are awful. Any occupational health and safety person would probably get a heart attack by just seeing it. The environmental damage is massive. There are a lot of chemicals that leak into nature. But as the process is carried out by poor workers, everything that has any value to anyone is for sure recovered and recycled. Now that I've sort of cast a shadow of doubt on circular economy, of course the question is it any good? Well, my subjective view is that of course it's good, it's a great idea, but it's also a buzzword. It doesn't solve all the problems. It is more important always to understand the processes without labeling them as linear or recycling. All cycles have both of them. So what goes in, what comes out? What kind of resources go in, what kind of pollution or whatever comes out? And not all resources are non-renewable. For example, water use is not a problem in Finland. Always compare at least 2 scenarios. There is no comparison in one scenario. And there are a lot of parameters that need to be compared: carbon footprint, water use, pollution, biomass use, inorganic material use, energy use, and so on and so forth. There is no such parameter as use of virgin material. It may be good, it may be bad, but please consider the full life cycle until the end of life in all comparisons. And when you make the comparison that way, the result is usually difficult because you end up with different advantages and disadvantages for different processes. For example, recycling copper, a metal, it actually has higher carbon footprint today than using virgin copper. On the other hand, virgin copper, when it's dug out of ground, then it uses a lot of minerals and you get a lot of rock and possible local pollution and so on. But sometimes the most important problem of virgin materials is, for example, pollution, which can be fixed. Sometimes it's something that cannot be fixed. In general, circular economy makes most sense with resource or energy intensive materials which are easy to recycle. And also, if the answer to the end of life is landfill, then something needs to be done. Then something is broken in the waste management side. But let's look at this by looking at some cases. First, a plastic bag. What would you use for shopping groceries? Plastic bag, paper bag, cotton bag? This was studied in the Opticossi project about 15 years ago. Beware, the data is old, 15 years old, but the basic things are there, so it's probably in the ballpark, but don't rely on it too much. So a single-use plastic bag is around 30 grams of carbon dioxide. At the end of its life, it is incinerated in the waste incineration, which gives energy. The value of this energy is not easy to determine, but in practice, the bag replaces waste imported from another country. And yes, we do import waste from other countries because we have so much waste incineration capacity. Or then the bag is recycled as plastic, which recovers maybe half of its emissions or energy bound to it. Of course, it can be used several times, and if the plastic bag is manufactured of recycled plastic, so we have sort of full cycle, we use a recycled plastic bag and we recycle it, then the estimated carbon footprint is only 10 grams of carbon dioxide per bag. And of course, the end of life, if it's not recycling, then it can be waste incineration, possible by using it as a waste bag, which then again replaces another plastic bag. We can also make the bag out of biodegradable plastic, but the emission is higher, maybe 60 grams of CO2. Also, these biodegradable plastics are a bit out of fashion due to microplastics. They are no good for biowaste, they are no good for composting. It's a bit unclear what they are good for because they can decompose into microplastics. A paper bag is, of course, an option. It is almost always made out of recycled fiber. Just for cost reasons, the estimated emission is the same as for our virgin plastic bag, 30 grams of CO2, no difference there. The end of life is either incineration, recycling as a fiber among cardboard waste, or as bio-waste bag. All recover some of the emissions, but again, it's difficult to estimate. Anyway, it will be lower than that 30 grams. And finally, we have the glorified cotton bag. The emissions of the cotton bag are around 2 kilograms of CO2, 2,000 grams of CO2. It will be used many times, many times hopefully, and the end of life is either through fiber recycling, which is not that common, or incineration. The former case, fiber recycling recovers some of the emissions, but burning very little because there is not that much mass in the bag, so the end of life is not that important with the cotton bag. So which one is the best? By these numbers, a cotton bag needs to be used 50 to 100 times before it's on par with a virgin plastic bag. If we take a recycled plastic bag and dutifully recycle it, this may be 200 to 400 times or 500 or even more times, which is probably unrealistic for most bags. But plastic has always the possibility of creating microplastics. Paper doesn't, cotton doesn't. And paper recycling is much better than plastic recycling. So it might be that the paper bag could be the winner here, but not for emission reasons, but due to microplastics. Now, if you sell any one of these, or if your ideology is towards one of these, if you hate plastics or if you love to have cotton, then you can certainly find the numbers in literature that will say that you are right, and you can choose the numbers. But the point here is that single-use bags are much more linear economy, but not necessarily any worse. They might be even better. And what is my solution? My solution is a polypropylene bag which can be used several times. So it's this one. It has been through hundreds of cycles. And it has met Mr. Washing Machine a couple of times. The carbon footprint is lower than that of cotton, but maybe 10 times that of single-use virgin plastic bag. It's not very recyclable, it's not monomaterial, so I suspect that its fate will be quite hot, but then again it burns well. It's very useful fuel in waste incineration. And now after all this, you have no idea which one to pick, right? Because any one of them can be the best. Then just think one thing, we're talking about grams of emissions, maybe 10 grams of emissions per bag, whereas the food in it is in kilograms. So where should we concentrate our focus? Packaging is important, but seldom very large part of the footprint. Recycling is not a new thing. That's something that has been done forever. Let's look at some examples of practical recycling today. Paper and cardboard first. The recycling rate in Finland is whopping 94% and the volume is around 100 kilograms per person per year. This recycled fiber replaces virgin fiber out of wood, and it's usually the fiber it replaces would be mechanical pulp, which is quite energy intensive, a great thing, so it saves resources, it saves energy. A single fiber goes in average 5 times around, and after that it's too short, so it shortens every time and weak to go around, and then it ends up in energy production. Hot fate again. Aluminium is another example. Over 90% of aluminium is recycled because it has a relatively high scrap value. It's about €1 per kilogram. You don't throw that away, do you? Aluminium doesn't degrade in recycling. Recycled aluminium is as good as new and it can be sold as virgin material. And that's typical of metals. You just melt and you reuse them. No structural damage, no nothing. However, melting of course requires some energy. For aluminium, recycling uses about 95% less energy than virgin production because aluminium refining is actually very energy intensive. And interestingly, about 75%, 3/4 of all aluminium ever produced since 1885 is still in use. So it recycles extremely well. And then we have an ugly duckling here, unsorted domestic plastics. A lot of it, but the collection rate is low. In Finland it's about 40%, globally less than 10%, and a lot of it ends up in oceans and rivers. Majority of collected waste is not recycled as material, it's incinerated. And the logistics is difficult, it's high cost because those plastic packages take a lot of volume, so it's expensive to recycle. Recycling plastics doesn't make any economic sense, but it might make environmental sense. Plastics are truly a problem. The main problem, sort of contradictory thing, but the main problem with plastics is that they are very, very, very inexpensive. They have a lot of other good properties as well. On the other hand, they use fossil resources, and the problem with microplastics is a difficult one. So what should we do? Should we stop using plastics, create better recycling, just burn them after use? I think the answer is yes. First, packaging industry is huge and there are different lobbying forces. Politicians may do something just to feel good. But it seems that there are several problems and several possible solutions. First, clear monomaterial, non-colored, which has only one plastic type. Thermoplastics like polyethylene, polypropylene and so on, the typical ones, they are easy to recycle as it. You just melt them and you get good new material. The problem is that this doesn't cover a lot of domestic plastics. We have too many multi-layer packages with very different plastics in them combined and beautiful printing, and a lot of it is not because it would be technically better to sort of protect the contents, but because it looks better. And all this hinders recycling. On the other hand, plastics are a great fuel, so if you have difficulty to recycle plastics, then the answer might be incineration. Without plastics, burning, so the waste incineration of domestic waste would be much more difficult because there is not that much something to burn. And then there are some new chemical recycling methods where the plastics are chopped into smaller molecules, pyrolysis, which creates oil-like thing from plastics, a sort of new thing, or gasification, where plastics are converted into so-called syngas, which is hydrogen and carbon monoxide, and all the oil industry knows, or petrochemical industry knows what to do with syngas. You can synthesize almost anything out of it. But when you break these long chain plastic polymer molecules apart, you get small molecules, you lose a lot of energy, so that's not a very energy efficient process. And then one thing is that machine sorting of plastics is getting better. So when you have mixed waste, you can sort it better to polypropylene, polyethylene and so on. So you can get higher value outcome of it, more pure plastic out of it. So there is some hope of better plastic recycling, despite not all problems having been solved. While the current domestic plastic recycling may actually have a negative environmental impact due to high energy use in the collection and recycling phase, it may still be good from the point that it teaches the consumers to recycle plastics, and that is important if we want to have real recycling of plastics. But then again, remember the order of actions. First, don't use. Second, use only clear monomaterial. And third, recycle. Use multi-material, printed, etc. only when really needed, and then incinerate or use chemical recycling. But let's take a simple material, water. How important is it to save water? Well, what would be, this is a glass of fresh water out of a tap, what would be its carbon footprint? It depends a lot on location, but this is from Turku. Then the journey of the water is a long one. It originates from a river, which flows through a lot of agricultural land, and this river is something that you could describe as a Jesus water, because you can almost walk on it sometimes. So first the solids are removed, and then the water is pumped 30 kilometers to Virtaankangas, a place where it's pumped onto a ridge, and it filters through the sand in that ridge. This creates artificial groundwater, which is again collected into 40-meter deep wells, and the water flows through 60 kilometers of tunnels into Saramäki, where there is a bedrock reservoir for water. Now the water has been filtered through a thick layer of sand. It has traveled about 100 kilometers, and there the water is finally chlorinated and pumped into the network, and actually it's very, very high quality water at that point. So the not so attractive river water becomes very fresh tap water through a lot of steps. So this must consume a lot of energy and resources. So what is the carbon footprint of the process? Well, the carbon footprint of the end product, cold tap water, is 180 grams of carbon dioxide per cubic meter per 1,000 liters. So a glass of water is worth 0.2 liters multiplied by 0.18 grams per liter, which is what? 0.036 grams of CO2, 36 milligrams of CO2. Well, that's practically nothing. So no worries about drinking a glass of water. But this changes if the water is heated. A 5-minute shower needs approximately 2 kilowatt hours of energy. That might be district heating, that might be electricity. And the emission is in the ballpark of 100 grams of carbon dioxide with Finnish energy, be it district electricity, but it could be double that, closer to a kilogram with, say, German energy. So the carbon footprint of the shower water in Turku would be around 10 grams of carbon dioxide, so it's not very significant, it's close to zero, but heating is the important thing. So the conclusion is that using cold tap water in Turku is not a big source for carbon emissions. And if you do that in Helsinki metropolitan area, the emission is a small fraction of that. So it's even lower. Helsinki metropolitan water might be one of the lowest emission waters in the world. But this is in a place, in a country where there is a lot of fresh water available. Globally, the situation may be very different. If you produce the water by reverse osmosis from seawater, then the numbers are quite different. And then we have the final recycling example, which is EV batteries. A lot of lithium batteries are needed in electric vehicles, and there have been voiced some serious concerns regarding the availability of materials, especially are we going to run out of lithium? Well, to understand deeper, the options, of course, are materials from existing mines. Well, it's not actually today mines, it's sort of more like shoveling lithium salts into somewhere. So it's very, very easy to get lithium at the moment. Then we can have materials from new sources, for example seawater. There is a lot of lithium in seawater, however the concentration is low, which means that it's not easy to extract it from the seawater. And then we have recycling, which sounds like a no-brainer. But the current state of battery recycling is that we have the so-called black mass, which has lithium, nickel, cobalt, manganese, graphite, all important battery minerals or materials. What happens to it? It's incinerated, it's burned. There are pilots to do better, but why do we burn it? Few reasons. First, the volumes are still very small because very few electric vehicles have reached the end of life. So there is no material flow to be recycled with profit. Then Virgin materials are not very expensive as you can shovel them out of somewhere. Recycling is very expensive. Old car batteries are also very sought after, not for recycling but for reuse, because they can be reused as battery cells or battery modules or as grid batteries. A lot of reuse there. So while there is a little recycling, there is a lot of circularity in this case. Yes, we burn some of that black mass, but then if we look at the volumes and the flows of materials, that is a very, very small fraction of everything. And then we may get sodium batteries, which may change this completely again, because sodium is something that you have a lot of it in seawater, it's easy to extract, and if you can use that in batteries, you have an endless source of sodium, no point in recycling. This is all about circular economy, which is not that circular, but still very important. I would just like to remind you that this is a field with very poor availability of solid data and some quite incredible claims, so beware, double check, triple check your data if you are in this field. Thank you very much for watching. See you next time.